Midterm coming up, so I always like to use a week to kind of step back and re-examine some of the types of problems that I hopefully have taught you. So you'll find on Blackboard that there's been a couple of midterm study guides, part 1 and part 2, that have been uploaded. The way I would recommend that you do these is you download the documents, you try these by yourself, and then once you work the problems, then log on, watch the videos, and see if you got them right. I think that's it's conducive to learning, and it kind of simulates what you're going to run into on the midterm. All right, so let's get busy, guys. Let's do it. First question says, in the United States, the total alcoholic beverage sales, I don't know where I got this problem, were 119.1 billion in 2003, 132.3 billion in 2005. Sounds like we drink a lot. Let T represent time, where T equals 0 corresponds to 2003. So guys, I know that I'm going to have the order of pairs 0, 119.1, and then 2 years later in 2005, I'm going to have 132.3 billion. Now, gang, I'm going to use my calculator to solve this. I think it's just easier. If you were taking a calculus class from me, I probably wouldn't allow you to do this. It's not like I would, stand over you with a billy club and not let you do it, but I would expect more in terms of symbolic manipulation. But in an applied course, it makes sense to me to teach it this way, okay? So guys, I need 0 and 2. And then to correspond with 0 and 2, I need 119.1 and 132.3. All right, once I get that, just go second function quit and go to stat, go over to calc, come down to linear regression, and just go left parentheses L1, comma, L2. Now, guys, if you have a different operating system, we should know how to do this by now because I put up a lot of videos. But anyway, in X list, you'd put L1, Y list, you'd put L2, and pretty much do the same thing. So, gang, what we get here is actually we get some more information I'm used to. This R and R squared, this is just the correlation coefficient and the coefficient of determination. Ignore that in the context of this problem and focus on the A and the B, which are the slope and the intercept, as we've talked about before. So we're trying to find A of T here. So we want the amount of alcohol sales. So that's why they used A as a function of T time, the number of years beyond the starting point of 2003. And our calculator gives us that that's going to be 6.6 T plus 119.1. All right. So part B, estimate the alcohol sales produced in 2015. So this is going to be equivalent to, again, T equals 0 is 2003. So 2015 is 12 years later. So we're going to be approximating, be calculating A of 12. So we're going to have 6.6 times 12 plus 119.1. So gang, I'm going to use my calculator there, as I would expect most of you to do. So I'm going to have 6.6 times 12 plus 119.1. So is that right? 6.6 times 12? I was expecting something different. I don't know why. Not sure. So $198.3 billion we would expect to be spent on alcoholic beverage sales in the United States. Now, part C is a little bit different. It says if the model remains accurate, then when would the alcohol sales reach 300 billion? So I want my function value to be 300. So I'm going to have 6.6 T plus 119.1. So guys, as you would expect, we're going to subtract 119.1 from both sides. And when we do that, we get 180.9 is 6.6t. And we're going to divide both sides by 6.6. And we get t is approximately 27.4 years. So we would add the 27.4 to the 2003, since that's the starting spot. And this is going to happen in about the year 2030. So about 15 years from now, if this model remains consistent. And that's something that you just don't know. All right, gang. Number 2, at a break-even point of 500 units sold, the variable costs were $125 and fixed costs were $10,000. Now, guys, when we see this break-even point of 500, what I know right off the bat is that my revenue at 500 is the same thing as my cost of 500. I also know from reading the problem that the variable costs are 125 and the fixed costs were 10,000. So my cost function, or my cost as a function of Q, and you can call this X, you can call it Q, you can call it A, cost amount, cost quantity, cost X. You can call this whatever you want it to call it. Just be consistent and pay attention on my math lab to the variable that they want you to use. But anyway, I have 125Q plus 10,000. Now, I know that the C of 500 is playing a role in this problem, so I'm just going to go ahead and calculate C of 500. And when I do that, make sure we got the right number of zeros. We get 72,500. So I know that my revenue of 500 has to be equal to C of 500 is 72,500. So I know that my cost at 500 and my revenue of 500 has to be 72,500. Now, I can use what I know about a revenue function, which tells me that the revenue can be calculated by taking the price at which it's sold times the quantity. Well, the quantity is under investigation here is 500 because of the conditions of the problem. So I know that I can find the price at which this unit is sold by taking 72,500 divided by 500. So gang, they're selling this product at $145. So let's think this through. They're selling it at $145. They've got $125 in each unit. They're selling each unit for $145. So my profit per unit is 20 bucks. So what will the 501st unit sold to profit contribute to profit? 20 bucks. What will the 502nd unit contribute to profit? 20 bucks. What will the 552nd, the 6,000th unit sold contribute to profit? Contribute to profit 20 bucks. Kind of a hard problem. Students struggle with that because there's a lot going on back here. Guys, it's just one of those things you gotta you just gotta study. I mean, sometimes that's kind of what we expect of you here. All right, minor league baseball park has 7,000 seats. Yada yada yada. I don't even care about that right now. When I start reading this problem, I can almost guarantee this is a systems of linear equations. and I am going to go directly to the last sentence and see what they're asking me to find. Okay? So when I go to the last sentence, I get some more stuff, number of box seats, 1/3, whatever. Then how many seats of each type? So guys, right now, I know my variables have to be types of seats. Now I'm going to go back into my problem and read, and I see that there are box seats, grandstand seats, and bleacher seats. I think a lot of people miss these problems because these types of problems, at least, because they don't get started out correctly. And I consider myself to be pretty good at this kind of stuff because I've studied it and taught it for so long. But and this is a short problem, but some of these problems, man, you get into like 7 or 8 sentences, and my mind just gets overwhelmed with all the information. I've got to go to the last sentence first, find out what I need. I'm ultimately trying to solve for. Therefore, that has to be my variables, and work from there. Now, next thing I do is I go back in and start reading very carefully the information that I'm given. Well, I see right here, minor league baseball park has 7,000 seats, so I know that the sum of all the seats sold has to be 7,000. All right, next thing I do is I get into my revenue. Well, box seats are $6. That's awful cheap, even for a minor league baseball park. 4Y and 2Z, and my total revenue is 26,400. Now, keep in mind, guys, I have 3 variables. I must have 3 equations. I only got 2, so I got to search a little harder and work a little harder to find that third equality. Well, I get that in the last sentence. It says the number of box seats, so I've let that be X, is 1/3 the number of bleacher seats. Well, bleacher seats is Z. Now, this number over here is 1/3 the bleacher seats. So do I multiply this by 1/3, or this by 1/3, or this by 3, or this by 3? Well, that's the hard part. So let's just think it through and just put some real live numbers up here. Let's say the number of box seats, and we want something divisible by 30, is I don't know, let's just say 3. We know it's not going to be that. And the number of bleacher seats would be what? For the box seats to be 1/3 of that. Well, it'd be 9, wouldn't it? So how do we make these two things equal? We multiply the smaller by 3. So the number of box seats, this over here is 1/3 this. So we could multiply this by 1/3, or we can multiply this by 3. Whatever you do, whatever you want to do, okay? I'm going to multiply this one by 3, and it wouldn't matter. All right, gang, next thing I want to do is I want to create my augmented matrix. So I have a 1, 1, 1, 7,000, 6, 4, 2, 26,400. And guys, I got to put this in terms of X and Y's and Z's in my numbers. So I'm going to have a 3. I don't have a Y. When I bring this Z across, it's going to be negative. And that leaves me with nothing over here as my constant. Now, I'm going to put this in my calculator, just as we've done before. And I'm going to use matrix A, and I need a 3 by 4. So I have a 1, a 1, a 1, a 7,000. I have a 6, a 4, a 2, 26,400. And I have a 3 and a 0 and a -1 and a 0. Now guys, make sure on that -1 right here, that you use this negative down here. Don't use your subtraction sign. If you do, you'll get an error. So let's go second function quit just like before. Go back into matrix, go over to math, and find this RREF command that works these types of problems for us. Go back in, get your matrix, and you can see that we have 400 box seats. We have 5,400 grandstand, and we have 1,200 bleacher. And let's see if the conditions work. Well, it does add up to 7,000. We can test our revenues. So we'll take, well, you guys can't see that, can you? So we'll take 400 times 6 plus 5,400 times 4. And then we'll have plus 1,200 times 6. And sure enough, we don't get the right answer. Why not? 6, 4, and 2, 5,400, 1,200 times, oh, I messed up here. That should have been a 2. So 26,400. All right. And then the next condition was the number of box seats, which is 400, needs to be 1/3 of the number of bleacher seats, which is 1,200, and it is. So guys, we got this right. I mean, I knew we'd get it right, but sometimes it helps just to step back and test it out. All right, gang, number 4, cost of making 20 radios, 6,800. Cost of making 50 radios is 9,500. The relationship is linear, and the radios are sold for $225. So, guys, for the cost, the first thing I have to do is I have to see that I have the relationship or the order of pairs 20, 6,800, and then I have the other 50, 9,500. So I'm going to come up with my cost function using my calculator. Somebody says, why use that? I mean, clearly I can do these without the calculator, and some of you probably can too, but this is an applied course, so we'll make the calculations easy, and we'll spend more time on doing cool stuff. All right? So let's go into stat, go to calc, go to linear regression, and go again L1, comma L2. And we'll see that our cost function is 90Q plus $5,000. So I know from this that my variable costs are $90 and my fixed costs are $5,000. Now I can also see very quickly that my revenue, they're selling this product, these, what is it again, radios? Yeah, they're selling the radios for $225. So they must be pretty good radios, because you can buy a really good radio from Bose for $225. But so I'm going to have $225. Now what will happen, guys, is a lot of people will stop right there, a lot of students. And that's just wrong. We're not saying that the revenue for any amount of quantity is a set $225. We're saying the revenue per unit is $225. Okay? Now, we had to find this information, the revenue and the cost, to work the problem to find the break even. So guys, remember the break even can be found one of two ways. It can be found by finding where our revenue is equal to our cost, or it can be found by finding where our profit is equal to 0, where the profit is the revenue minus the cost. Now I'm going to work it both ways just to kind of make a teaching point here. So the first way I can do that is just set the 90Q plus 5,000 equals 225Q equal to each other. I'm going to subtract 90Q from both sides. And then I'm going to divide both sides by 135. So I get my quantity at 37.037. So we'll report that as 38 units. Now, another way to do this is to find that our profit function is our revenue function, which is 225Q, minus my entire cost function. So I have 225Q. Now I'm going to distribute the negative through to each term in the cost function. And I get 135Q minus 5,000. Now if I want to set that equal to 0 to find out where my profit is 0, because profit being 0 and my revenue and cost being equal to each other is the same thing. So I add 5,000 to both sides. Look familiar? Same thing, right? And again, just demonstrating that setting your revenue and your cost equal to each other and solving for Q, or solving for Q where the profit function is equal to 0 lends the same answer. So guys, the answer is 38 units. That's not bad, is it? But those are expensive radios, apparently. Now, how many radios must be sold to realize a profit of 250,000? Well, guys, we've already seen that our profit is 135Q minus 5,000. So we just need to see when that's going to be 250,000. Well, what am I going to do? I'm going to add 5,000 to both sides, so I have my 250,000. And I'm going to add 5,000. So guys, be careful with the zeros. Make sure we get enough. And then we see that we need to divide both sides by 135. So we need 1889 units or radios to be sold to realize a profit of $250,000. Problem number 5, where P is in dollars, let the supply and demand for sugar be given as the following. Now notice P is our Y. So we have, for both the supply and the demand, we have our quantity first and our price second. So first thing, it says graph these on the same axes. And I put this in here, and I gave you a different spin on supply and demand just so we could practice a little bit trying to come up setting our axis. All right? So I'm going to come in here, and I'm going to put in my supply first, and it's what, 1.4. And I can't use a Q. I have to use an X, just the way the calculator is set up. Minus 0.6. All right. My demand is negative 2Q plus 3.2. Is that right? Yeah. Now, gang, I got to figure out how to set up my window. Well, if you think about it, X's in this case are quantities, and quantities can't be negative. So it makes sense that I would set my X min at 0. Now, in terms of where I set my X max, I'm going to just think of this as Y equals And I'm just going to just try to get an indication of how the x's and y's behave here. And I can see that my x-intercept here would be when y is equal to 0. So I can kind of mentally think about bringing this 1.6 over here, making it a negative 1.6, and solving for x and y 0, because that's going to tell me where my line goes through the x-axis. So it gives me just a little bit of an indication of where these values should be. And if I do that, I'm going to get, let's get out there and do that. So we're going to get negative 0.6 divided by negative 1.6. So I get a very small value here in terms of quantity. So I can tell right from that when I set up my window, I'm going to go up here to about 10 and see what happens. I can adjust if I get it wrong. I'm going to go 1, and then my y min, y max, I don't care. I can just put something as long as my y min is less than my y max, because I'm going to use a function on my calculator that will reset that. So the important thing here is I have a pretty good indication of what's going on with my x's. Okay? Now, so when I do that, I can go zoom and come all the way down to, well, I've got a bunch of stuff down there. Zoom fit. And what this is going to do is going to adjust my window according to the x's that I've given. Now, guys, we may not get it right. And I look at this and I think about my y's. My y is price. So I really don't need to be thinking about my y's that are negative. So let's graph this thing again. Now, this is strange. I don't know what in the world is going on for sugar. It must be pounds of sugar, or millions of pounds or something. But really, I've got 1, 2, 3 to get my equilibrium point. I really don't need to go much more than over to x equals 4. And we get that as our supply demand. Kind of goofy looking, but it's what it is. Find the equilibrium point. All right, so let's just go second function calc. Come down to intersect and go enter, 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 and enter again. It'll give us our intersection. So our x is what, 1.12. And our y is 0.96. Now, this is kind of a weird problem because I don't know what sugar is being provided in, but I'd say it's probably some sort of millions of pounds or something. So anyway, the equilibrium point, which has the price second and the quantity first, tells us that the supply and the demand for sugar happens when the quantity is 1.12, whatever we're measuring this is, and the price is 96 cents per, 96 cents, yeah. On what interval does the supply exceed the demand? Well, guys, the supply is, the supply is this 1.4, so we know it's the one with the positive slope. So it's got to be this one right here. Well, everything to the right of our equilibrium point, our supply is higher than our demand. So I can say from the interval the supply equals the demand, well, from 1.12 all the way up to infinity. Okay? Easy stuff, guys. All right. Got quite a few questions about this particular problem. No, I didn't. It was another type of problem. So write the system of equalities that corresponds to the augmented matrix. So you got to remember, guys, these are x's, these are our y's, and these are our constants. So the first one says we have 2x minus 9y equals 29. And this one says we have 3x plus 8y equals 22. So we usually start out with this form and create this, but this problem gives us this form and wants us to undo what we take kind of naturally in this class to create the system of linear equations. Number 7, solve. Well, guys, easiest way to solve these things, I think I've impressed upon you in this class, is to use an augmented matrix. So guys, remember, I need my x's, my y's, my z's, and my constants. So the first one is in nice form. The second one is in nice form. And the third one is a mess. So we know here we got no x, we've got 1y, we've got 1z, and our constant is equal to 3. Now, if we can put this in our calculator without doing something goofy, we'll be able to solve the problem. So 3 minus 2, 1, 6, 11, minus 20, minus 1, 0. Somebody asked me one time, do I have to put the zeros in there? Oh, I don't know. What about that millionaire? I think that millionaire cares how many zeros. Do we need to put those zeros in there? Probably do. Otherwise, I got $1. 0, 1, 1, 3. All right, gang, let's do what we've done quite a few times before. And the solution is 2, 1, 2. Guys, our solution is always on the last column. So our solution is x equal 2, y equal 1, z equals 2. Now, let's just do some mental math and see if that does seem reasonable. Well, up here we get 6 minus 2 plus 2 equals 6. That's true. Here we get 11 times 2 is 22, minus 20, minus 2. That's certainly 0. And then we need y plus z to be equal to 3, which it is. All right, gang, number 8. Solve the following. Students are flipping out on me on this type of problem. You should not be. Let's think what this is. This is multiplying these matrices. This is x minus 4y minus z equal negative 5. This is 0x plus 3y plus z equal 7. And this is 2x plus y plus 0z equals 10. Now, if you don't know what I did there, you need to go back and watch one of the previous videos. When I introduced multiplying matrices, we talked about linear combinations. So I'm taking 1 times x plus negative 4 times y plus negative 1 times z to get this. Okay? Or just remember it. So gang, what do I do when I get in this situation? I just create an augmented matrix. This matrix is going to be 1, negative 4, negative 1, negative 5, 0, 3, 1, 7, 2, 1, 0, 10. Look familiar? Yeah. This is just these numbers, and this is just those numbers. That's exactly what we're doing as we've seen in these previous problems. This is a system of linear equations which uses augmented matrices to solve them. And this augmented matrix is nothing more than what we call in mathematics your coefficient matrix. and your response matrix. Well, that'd be a response vector. And it all goes together in one big matrix, called our augmented matrix, to solve this. So gang, let's, I'm going to go through this one pretty quickly. So I still need a 3 by 4, so I have 1, -4, -1, -5, 0, whoa, I have no idea what I did there, 0, 3, 1, 7, and 2, 1, 0, 10. Get out of there. Guys, I'm going to go second function entry because I need to do the same thing I had before. So gang, our solution is 4, 2, 1. So x is equal to 4, y is equal to 2, and z is equal to 1. Now I go through these a little quicker than I would in a class because in a class you don't have the opportunity to stop me, to pause me. Actually you would, because you could just say, hey, Dr. Darbo, slow down, and I would. But in this type of presentation, all you got to do is hit pause. All right, gang, this is a little bit tougher problem right here, I was going to tell you. A couple invests $5,000 at 3.5% interest rate. How long would it take for the investment to double if the interest is compounded annually and continuously? Well, guys, the interest rate formula that we're going to use ad nauseum is this, and when we are compounding annually, that means that n is equal to 1, so this becomes a times p plus times 1 plus r over 1 raised to the 1 times t power. So we know that we invested 5,000. For this thing to double, that means it would have to turn into 10,000 times 1 plus r, which was 0.035 to the t power. So I'm going to divide both sides by 5,000, so I think there's no surprise we get 2 here. And this is 1.35 raised to the t power. Now, what do I do when I get a situation like this? Well, I'm going to take the natural log of both sides. Next thing I'm going to do is I'm going to realize that when this exponent's up here, I can always bring it out and write it in front. So, guys, we have a property that says that the natural log of a to the x power can be written as x times natural log of a. Okay? So we have the natural log of 2 equals t times the natural log of 1.35. So I'm going to divide both sides by the natural log of 1.35. And I can see that t is going to be 2.3 years. That doesn't seem right, does it? Natural log of 2. Oh, shoot, guys. I messed up big time, didn't I? I got sloppy here. That should be 1.035. Gosh. Think that makes a difference? Yeah, I just kind of preached that zeros do make a difference. So, gang, I messed up. I got sloppy there. I'm actually pretty good at this stuff. So, yeah, 35%. It's not going to take long for your money to double. So, gang, we need to do this correctly. We need to take the natural log of 2 divided by the natural log of 1.035. And come back to the real world. It's going to take 20 years. For your money to double. Okay, that was fun. Sorry about that. Continuously compounded. Here's the formula we'll use here. So same information, our money doubles, which means it grows to $10,000. We have this E. Our rate is I should put 0.35 just to mess with you guys. 0.035 times our time. Now, continuously compounded, we're going to expect it to double a little bit quicker, but it's not going to double a lot quicker. So guys, I want to divide both sides by 5,000, and I think we all see that that's going to lead to 2e to the 0.035t. I'm going to use this again. This is going to be a property that we're going to use over and over and over and over, so that's going to bring this out. Shoot, what am I talking about? We got to take the natural log of both sides. Kind of hard to apply this property if we don't have the natural log of it, right? So now we're going to have the natural log of 2 equals 0.035t times the natural log of e. Now, guys, the natural log of e is nothing more than 1. And you can prove that to yourself by just going the natural log of e to the first power. And you'll see that it's just 1. Okay? Ultimately, we get the t, if we divide both sides by 0.035, it's the natural log of 2 divided by 0.035. And just a little bit earlier, not much. About, what, 2/10 of a year, which would be about, what, 3 months, something like that. All right, gang, last problem on this. Convert this exponential form to logarithmic. So guys, remember, we have three things here. We have log base b of the number that it takes to raise the power to the base to get. Base, the exponent, the number we get when we take the base to that exponent. So guys, our base in this case is clearly 2. Our exponent is clearly x. And the value we take to raise is 64. Now, I just tell you to convert that. Could you solve that? What if I ask you to solve instead of? It'd be pretty easy, wouldn't it? If we want to solve 2x equal 64, we could probably just see that 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, and times 2 is 64. So we could just count the number of 2's, right? But another way of doing it, a more systematic way, is we could take the natural log again of both sides. Realize that this can be divide both sides by natural log of 2. And put that in our calculator, and we're going to get exactly what we thought we would. We'll get 6. So 2 to the 6th power is 64, which tells us that the the log base 2, 64, is the exponent of 6. All right, gang, take this to exponential form. So again, this is our base. This is our answer. And that's the answer to the base raised to that exponent. Okay. So there's no variable in there to solve for. It's just a matter of converting. All right, gang. That was fun. All right. hopefully you tried this before you got started, and you did well. All right. So guys, that's it. Take care.